Okay, so this is question 17. We have this circuit here, and we want to find out the transfer function. Okay, so we have a load that's 3K, so we are going to consider that this load is connected to the circuit, so it's loading the circuit, okay? Otherwise, you can consider it as an open circuit, which means that RL is infinite, so it's just a matter of, once we calculate the transfer function, substitute RL as infinite, but uh, and at this analysis, we are going to consider as if it is part of the circuit, so it's loading the circuit. Okay, so part A, we have to find the transfer function of the circuit in terms of R1, R2, RL, C1, and C2. For part B, given the component values that we have in the circuit, what's the value of the transfer function at 1 megahertz? And then C, we have to make a Bode table, so with like some values at some specific frequencies, and then calculate the magnitude in dB, which is the G equals 20 log 10 of the magnitude, and the phase. And then from that table, we basically draw the Bode plot. Okay, so how do we analyze this circuit? So I think the best approach for this circuit is actually using KCL. Okay, so we can name this node here as node X. So we have Vx here, right? And then exactly here we have V out, and here we have Vi, or in our case, I'll call it Vi, but it's the same as Vs of j omega. Okay, so everything here it's going to be at in the frequency domain. Okay, so in this case we have to convert those capacitances to reactances, and if you remember, to convert um, from capacitance to reactance, a capacitor, its Xc is equals to 1 over j omega c. Okay, so let me just erase here this j, it's a little bit weird. So j omega c. Okay, that's the so we have resistors, they're the same in the time domain and the frequency domain, uh, and for capacitors here we have just 1 over j omega c. Okay, so that's it. We have just to analyze this node here, right? And this node here. So we have like two equations, and then we can basically manipulate those equations to calculate the voltage transfer function. Okay, so let's start with node, let me see, let's start with this node here. Okay, so let's call this node 1, this node 2. So for node 1, okay, for node 1, we have V out minus Vx divided by R2. Okay, so it's this term here, this current. And for my analysis, we are going to assume that all the currents, they are leaving this node 1. Okay, so we have a current here, we have a current here, and another current here. Okay, so this current that's flowing from 1 to 2 is V out minus Vx divided by R2. So remember that we have to take this in terms of R's and C's, plus the current that's flowing through the capacitor C2. So that's equals to V out minus 0. So suppose we have a ground here. Let's select that node as a ground. So it's V out minus 0 divided by 1 over j omega C2, right? Uh, Plus V out minus 0 divided by our load, and that should be equals to 0. So from this equation here, we can write Vx in terms of V out. So if we isolate V out here, we have, so we can basically multiply everything um, by R2, right? So it means that we have V out minus Vx plus, uh, So it's J omega C2 R2 times V out plus V out times R2 over RL. That should be equals to 0. So this gives us Vx equals to V out that multiplies 1 plus R2 over RL. So this one here is 1, this is R2 over RL. This one is plus J omega C2 R2. Okay, so that's Vx. Now let's analyze the node 2. So for node 2, we have a current flowing here, a current flowing here, and a current flowing here, right? So for node 2, first current will be Vx minus Vi divided by R1. So Vx minus Vi divided by R1 plus Vx. So if you look at here, this current here, right? Vx divided by 1 over J omega C1 plus the last current Vx minus V out divided by R2. So plus Vx minus V out divided by R2, and that should be equals to 0. Okay, now we can substitute this Vx in the equation for node 2. Okay, and this gives us like an ugly equation. So now it's just a matter of like manipulating the variables here. But so if we substitute that equation in node 2, we get something that it's V out 1 plus R2 RL plus J omega C2 R2 minus V out plus V out J omega C1 R2 multiplying 1 plus R2 RL plus J omega C2 R2. Okay, and then this continues plus V out R2 divided by R1 that multiplies 1 plus R2 over RL plus J omega C2 R2 minus R2 over R1 V1 equals to 0. Okay, now if we manipulate this equation here by multiplying by R1, R2, and then isolating V out, we get our voltage transfer function. So the h of J omega, it's going to be, so we isolate V outs here, right? So we have V out here, and Vi here. So we isolate V out, and then we can take V out of J omega divided by Vi of J omega, right? That's going to be equals to 1. So 1 here divided by 1 plus R1 plus R2 divided by R load plus J omega. So I'm going to isolate the terms J omega and J omega squared. Okay, so J omega C1 R1 plus C2 R2, sorry, C2 R2 plus C2 R1 plus C1 R1 R2 divided by RL, and it continues, plus J omega, and that's squared, C1 C2 R1 R2. So that's the voltage transfer function. Okay, so this one here is the voltage transfer function. Okay. So that's the end for part A. Now for part B, if we substitute the values that we have, so this is for part A. For part B, if we substitute the values that we have, okay, the magnitude in dB is going to be approximately, so if we substitute in that equation and then evaluate it for omega equals to 1 megahertz, the magnitude is around minus 164 dB, which corresponds to a magnitude in linear scale that's roughly 6.3 nano, sorry, nanovolt per volt. Okay, so this is for part B. Now for part C, I have picked some values. You can check those values in the solutions that we have on CU Learn. So I picked frequency radian frequencies like 1, 10, 100, 1,000, 10,000, and 100,000 radians per second because I thought that was enough to basically describe the behavior of the function. So for part C, verify the solutions at CU Learn. Okay, so do that. You have like a table with all the values. Okay, I'll just mention them here just to like don't waste too much time talking about just numbers. Okay, so for the magnitude, we have this one here. So this is frequency. This is magnitude of h of j omega in dB. Okay, for the Bode plot. So 10 to the 0, and we have 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5 radians per second. Okay, and then I'll have here minus, so this is 0 dB, this is minus 20, this is minus 40, this is minus 60, minus 8, and minus 100. So from my table for 1 radians per second, I have something that it's minus 6 dB, so it's around here, minus 6 dB. For 10 to the 1, like 10 radians per second, it's still minus 6 dB. For 10 to the 2, it's minus 6.5 dB, so it's a little bit lower than that, which here it's almost 10 already, so I'll just put it over here again. For 10 to the 3 is around minus 17, so it's almost 20, minus 20, so it's around here. 10 to the 4, it's minus 51, so minus 51, it's around here. And then for 10 to the 5, it's minus 91. So you'll see that the difference between this point here and this point here is actually minus 40 dB. So at the end, this is the plot that we have. So let me put like a thicker line. So this is the plot that we have. And then from this point onwards, it's just like, so it's, let's just erase here. So from this point onwards, it's just like minus 40 dB per decade. Okay, so that's the magnitude. And then for the phase, we can kind of use the same scale here. So let me just draw here omega, that's the phase. So here, 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 here. 10 to the 4, 10 to the 5, so 10 to the 5. Here's 10 to the 3, and here's 10 to the 1, right? So we can draw the phase, and the phase starts at 0 degrees and then goes all the way up to minus 180. Okay, so just draw here 40, 45. So it's 45, here's minus 90, and here it's minus 135. Here's minus 45. So for 10 to the 0, it's basically 0. So it's up here. 10 to the 1, it's minus 2. So it's almost 0 here. For 10 to the 3, it's going to be minus 21. So it's something around here. Then for 10 to the 3, let me see. 10 to the 2 it's minus 20. For 10 to the 3, it's minus 104, so it's a little bit more than 90, a little bit less than minus 90. For 10 to the 4 is minus 170, so it's around here, right? And then for frequencies that are higher than 10 to the 5, it's roughly around minus 179, minus 180 degrees, so it goes all the way here. So at the end, the phase, it behaves just like, sorry. So just connect the points here. So it just looks like this. So that's the phase, okay? Of course, you have like better plots on the solution, so you can check that, okay? But otherwise, that's the solution for this particular problem.